So, we've been working on this phenomenon of the water strider and diving into the chemistry, especially the chemistry of the water molecule, for how this phenomenon can take place. So, you have access to these slides, but we were going kind of fast in class, especially at the end of class today. And with our test just around the corner, I wanted to kind of recap learning targets 2 and 3 and preview learning target 4, which we're going to talk about in class on Monday. Learning target 4. So, table of contents, a new feature in these slides here. You click on learning target 2, takes you to anatomy of an atom. Everyone's been picking up on this really, really well, so I'm going to go a little bit fast, but feel free to slow me down, to pause as you need to. Anatomy of the atom, the big things you need to know are these subatomic particles. So the neutrons and the protons are here in the nucleus of the atom. And then on the outside in these electron shells, we've got our electrons. So the electrons are contributing a negative charge, the protons are contributing a positive charge, and for the most part, when they're in their kind of normal state, I guess, the number of electrons and protons are going to be equal to each other. There's exceptions. You can deal with that in chemistry. For right now, electrons and protons are going to be in equal numbers to each other. And so then it's going to be no charge. That atom would have no charge to it. So then we asked ourselves, well, what element could this be? And we were able to look and see, well, it's got 3 electrons, 3 protons. The element that has an atomic number of 3, so in other words, that third one on the periodic table, is lithium. So that tells us that this is lithium. All right. Then we started to look at the electron shells, because this is also still part of that anatomy of an atom, because it's how those electrons arrange themselves. So in that first shell, the maximum it could even have is 2, but it wants 2. It wants 2 to be stable in that first shell. This really only impacts like hydrogen and helium. Helium has 2, and so it's happy, but hydrogen, poor little hydrogen, it only has 1 electron, and so it is completely missing 1. It would need 1 more to be happy. When we get into those bigger ones, so from lithium onwards, nucleus in the center, neutrons in the nucleus, which is the center, as well as your protons. And then we start to build up our electrons. So 2 in that first shell, but carbon has a total of 6. So we need to keep adding electrons. So we go to the next shell. We go 1, 2, 3, 4. Now we have a total of 6 electrons accounted for. But carbon's not happy because in that second shell, you want there to be 8 electrons in order for that element, that atom, to be happy, to be stable and not reactive. So carbon could have another one there, another one there, another one there, and another one there. And then it would be fulfilled. And that's pretty much learning target 2. Which brings us to learning target 3. Sorry, my dog just locked herself in the kitchen. 1 second. I'll edit this out. I hope. Alright. She's only happy if she's eating ice cubes. You want to say hi, Maple? Can you come here? Can you touch? Yes, good girl. Oh, you're just going to take it away? Okay. I can't see myself on the screen, so I don't know if you saw her, but I'll have to alternate between ice cubes and dog treats to keep her happy while I film this. All right, so we call those electrons in the outermost shell valence electrons. So that's a new vocab word for us. It just means the most outside electrons. And so hydrogen has 1 valence electron floating here. Carbon has 4 valence electrons. And it's not talking about the lack of electrons. It's talking about the electrons that they do have in whichever shell is the furthest out for that element. So that's learning target 2. Where this comes into play is these gaps, the areas where they're not happy, where they could have electrons added in order to reach a full outer shell. Those are potential spots for bonding, for them to react with another atom if they come into contact with it. And then it just depends on kind of which atom they come into contact with, which element, how they're going to bond. And so then we kind of talked into those structures. A very quick way to figure out the number of valence electrons is to use a trick on the periodic table. So kind of a weird analogy here, but I was comparing the periodic table to a castle because that's honestly when I first saw it, especially this rainbow version. That's what it reminded me of. So to me, we kind of have these tower situations going on either side, the middle of the castle and the moat. We're totally ignoring the middle of the castle, totally ignoring the moat, and we're just looking at the towers. Your chem teachers are probably going to hate that I use this analogy, but first tower, second tower here. So 1, 2, and then over here, 3, 4, 5, 6, 7, and then 8. They happen to tell you the number of valence electrons if that element is within those columns. And in this class, we will always just focus on elements that are within those columns to make our lives easier. Okay, so hydrogen needs one to be happy. Carbon is going to need 4 to be happy. So what happens if enough of them interact? We get methane. Methane is a molecule we're going to be talking about this year. It's made up of a carbon and 4 hydrogens, and they end up just sharing their electrons. So here, this hydrogen is going to share with this carbon and vice versa. Same thing here. They're going to share those. They're going to share, and they're going to share. And so what that means is that now this hydrogen's happy because it has 1 and then 2, the one that it's sharing with carbon. Same thing with this one, and this one. All those hydrogens are happy. And the carbon is happy because it's got 2 in the middle and then 3, 4, 5, 6 that it was contributing. And then 1, 2, 3, 4, the 4 that it's now sharing, this like joint custody situation with the hydrogen. And we call that a covalent bond. This is a very big vocab word for us. It's an important one. So it's describing this bond in which atoms form a molecule because they're sharing electrons. Sorry, her chewing the ice cube is so loud. Maybe I'll switch to treats. Okay. We talked about the fact that drawing something like this in class is insane. Like, you don't need that in your notes unless you want it. Like, maybe once is good on a quiz or on a test. I would never expect you to add that level of detail. So another way to draw this stuff that's helpful is to just draw the valence electrons and to just, instead of drawing all the shells, just kind of draw them around the letter of the element, the atomic symbol. Adding some videos in here, which obviously I'll skip over because this in and of itself is a video. And then we talked about sodium. And sodium only has 1 electron in its outer shell. Chlorine has 7 in its outer shell, and it only needs 1 more. So it's going to be just easier for sodium to give chlorine its electron to complete chlorine. And so what that means is that this has formed an ionic bond. Now, an ionic bond, they're not like physically tied to each other. What's going on here is it's just donating its electron. So sodium becomes positive because it has 1 less electron. So it has more protons now than electrons. If you look at these numbers here, it started with 11 protons and 11 electrons because sodium is number 11 on the periodic table. Chlorine started with 17 protons and 17 electrons. Now that chlorine has accepted this extra electron, chlorine is now more negative than it is. It's just more negative because it's got more negatives than it does positives. So we call it an ion. In fact, we call chlorine an anion and sodium a cation. You do not need to know those vocab words. All you need to know is that they get charged. And because they're charged, they are now attracted to each other. Just like we talked about with magnets, this is a very strong pull because it's a positive and a negative opposites attract. So they're bonded to each other through their attraction for each other. Now, something that's going to help you a lot that we talked about today is how do you tell the difference between a covalent bond and an ionic bond and what type of bond 2 atoms might form or 3 or more atoms might form to form a molecule? Here's the trick. Ionic bonds, it's always only going to be between 2 atoms, and those 2 atoms have to be a metal and a nonmetal. So kind of maybe make a flow chart for yourself. If it is 3 atoms or more, automatically covalent. You don't even have to worry about it or question it. If it's 3 atoms or more, it's covalent. So then you really only have to question if it's 2 atoms. So if it's 2 atoms coming together to form a molecule, you have to ask yourselves, is this an ionic bond or covalent bond? How do you figure it out? The easiest way is to ask, is it a metal and a nonmetal? It's ionic then. Or is it two nonmetals? Then it's going to be covalent. And how do you know if they're metal or if they're nonmetal? The periodic table. Conveniently enough, it's organized in a way that it'll show you if it's metal or non-metal. On a quiz or on a test, I do not need you to memorize these necessarily, but this colored version is very handy here. So hydrogen, this is kind of important. Hydrogen is a non-metal. So sometimes things will get a little bit weird when you're mapping it out and trying to see like, well, could hydrogen just take one or just give one away? If hydrogen just gave away its single electron, it would have no electrons. And so it's not going to do that. For the sake of our class, we are going to ignore the metalloids just because we can, because it's bio and not chem. Alrighty. So another way you can think of it too, we're really only going to look at these first two columns compared to like these two columns here, the 8 and the 9, like oxygen, fluorine, and what they have below them. Because think of it this way. Sodium, for example, has one valence electron. It's very likely that it and all of these other ones that have one valence electron are going to want to get rid of that electron. Same thing if they only have two. It's going to be a lot easier to just get rid of those two than it is to try and fill its whole outer shell. Similarly, over here, we've got fluorine. It only needs one, and so do all of these ones underneath it because they have 7 valence electrons. Oxygen, it only needs 2. So it's more likely to just take than it is going to be to share if it's combined with one from over here. So it's kind of like if those first two columns meet up with the 6th and 7th column, you're going to get ionic. And that's pretty much all the ones that we're going to be looking at in this class. All right, so that's a summary of the types of bonds. So ionic bond, it's going to be metal and nonmetal between two atoms. Covalent bond between two or between more atoms, and it's going to be those nonmetal and nonmetal. Hydrogen bond is different. We can talk about that later. Hydrogen bond is not a bond of forming a molecule. Hydrogen bond is how a molecule would interact with another molecule if there's hydrogens involved. And we'll take a look at that when we circle back to the big picture of this unit, which is water. All right, so then we ask ourselves, well, what's the deal with water? And I want you to really think about this because that's the whole point of this unit is water. This is not a chemistry class. We're not concerned about ionic bonds and covalent bonds in and of themselves. It's a means to an end, and that end is understanding the properties of water, because without the properties of water, we can't function. Like life cannot function. And so that's a trend that we're going to see throughout the year is this importance of water and how its properties, which are defined by its atomic properties, are so important for how our bodies work, for how larger ecosystems work, all that kind of stuff. I'm just chucking dog treats at her at this point. All right. So water. Water needs 2 electrons to be happy. Water forms when 2 of those hydrogen atoms are going to be attracted and share their electrons with oxygen. All right, we talked a little bit about this idea of diatoms, another vocab word. So diatoms, like oxygen, it's always hanging out with a buddy. Di meaning 2, and then atoms referring to atoms. So they're always hanging out with 2 atoms. No one ever calls or texts me, but apparently when I'm doing a video on atomic structure. Alrighty. So, method of bonding that applies to a water molecule. What is going on here with water? That's the whole point of this whole unit. Well, they're sharing electrons. We can see that they're 2 nonmetals. That's how we know it's covalent in and of itself right there. Like, yes, we could draw it, which would be super, we learned how to draw it. You could just draw it and see that it's going to make sense for them to share. But you could also recognize the fact that hydrogen and oxygen are both nonmetals. So when they combine, it's going to be a covalent bond. You could also look at it through the lens of there's 3 atoms, not 2. So it's already ruled out from being ionic, which means it's going to be covalent. Okay, so that poses a problem. We had said that water has these partial charges. That was one of the very first things you learned in this unit. But it's not made up of charged atoms. It's not a positive and a negative like with our ionic attractions attracting each other. No. So where's that partial charge coming from? So we said oxygen, partially negative, hydrogen, partially positive. And it's just because the electrons are going to hang out with the oxygen more. So this oxygen has this pull. The electrons are just fangirling over this oxygen. So it has to do with this idea of electronegativity. Electronegativity is a measurement of how much the atoms are going to attract electrons towards themselves, how attracted the electrons are going to be to that atom. The higher the electronegativity number, the more likely the electrons are going to gravitate towards that atom. And conveniently enough, you can actually look at the differences in these electronegativity numbers between two atoms within a bond to see, okay, are they going to hang out more with this atom or more with this one? And if it's less than or equal to zero point 0.4, it's going to be non-covalent. If it's greater than, well, really greater than 0.4, but 0.5, then it's going to be a polar covalent bond. So polar and nonpolar is only applying to covalent bonds. And it's not a full charge, it's this partial charge. Because they're happy. Like they're not charged. They completed each other's shells. They shared they're balanced. But there is still this partial charge going on just because of where those electrons are hanging out. So, electronegativity. The ones over here tend to have higher electronegativity, with hydrogen oddly kind of being somewhere in the middle. And we actually have this periodic table for you. It's already printed on your worksheet. So it has the electronegativity numbers on there. So let's calculate it for water and just confirm that water is polar, even though we know it is. All right. So you calculate the difference between the atoms within a molecule, and you would do this for each bond. So in this case, oxygen is 3.5. I'm getting that straight from this chart. That's electronegativity number. Hydrogen, 2.1. The difference, so we're going to subtract 3.5 minus 2.1, it's going to give us 1.4. So just a bond between an oxygen and a hydrogen, it's going to be 1.4 is that difference in electronegativity. So it's definitely greater than 0.4. So water is partially charged. Water is polar. Yay! We confirmed it. This is a great video that's showing us how electronegativity can help us determine bonds. Technically, if it has really, really high electronegativity, because let's actually look back at this chart here. Look at these that have kind of lower electronegativities versus these ones up here that have high electronegativity. Fluorine in particular, fluorine has, the electrons are very attracted to fluorine. It's very electronegative. So if you're combining one of these nonmetals with one of these metals, it's very likely that the difference between those two is going to be astronomically high. So electronegativity can actually also tell you if it's ionic, if it's beyond the threshold just for polarity. So we've confirmed it. Water is polar. Woohoo! All of that to basically get at that idea. But we needed to prove it using its atomic structure, prove it using the numbers from the periodic table, prove it using electronegativity, and prove that it is a polar covalently bonded molecule and not a charged ionic molecule. All right, I hope that helps with learning target 2, the structure of an atom. Learning target 3, figuring out if it's ionic or covalently bonded, so how the bonds are forming between atoms. And then we kind of previewed and kind of went over learning target 4, which is applying it to water. All right, good job. You guys got this. Email with questions. Bye.